Hello everyone, this is Hussein. Today we're going to solve MATLAB homework 1, question number 2. We're going to try to find the angle that this handle must be in order to lift this clamp arm by 30 degrees. So our initial condition for theta 2 is 90, and the final condition when this handle moves by 30 degrees, this one will be 6 degrees. I did start solving the problem here by the loop closure equation, and here's the vector representation for it, and here's the complex expansion for the loop closure equation, and here's when you separate the real and imaginary part. In this case we're going to have two equations, f1 and f2, and we're trying to find theta 3 and theta 4, which in our code will be q1 and q2. So we're going to go ahead and code these two equations and the derivative for it, the Jacobian matrix, to eventually solve for Newton-Raphson method, use the Newton-Raphson formula to solve for q3 and theta 3 and theta 4. So we're going to go ahead and start coding by clear all, close all, CLZ. We're going to first input our given values for our linkages. So R1 is equals to 25, and R2 is equals to 12, R3 is equals to 20, R4 is equals to 15. And we know that theta goes from 90 to 180 because this was the initial position and it goes for rotation. So theta 2 will be equals to 90 degrees, but we need to convert that into radians because the way functions work in MATLAB, the cosine and sine, they only accepts the cosine and sine, they only accept the radian values. Otherwise you're going to use cosine d, but we're going to make it easier and convert it from the beginning. So pi over 180. And in the problem, it said that for faster convergence, we're going to use the initial guess Q, 0 and 1 for the original configuration, and 1 and 3 for the reposition configuration. So we're going to use 0 and 1 for the initial configuration. So we're going to have Q is equals to 0 and 1. And the initial values of f, remember that we said that we cannot, for the Newton-Raphson method, we cannot start with values of 0, so we're going to give an initial value of 1 for f1 and 1 for f2. And we're going to start with iteration equals to 0, doing the same thing as in problem 1. Now we're going to start a while loop, while norm of f is larger than 1e to the negative 6. You can actually play with this value as you see it best fit in the equation. So it's going to try and error, see the best tolerance you can have. And we're just going to need to print the initial configuration. So I'm going to say fprintf initial configuration. Okay, this is just to display the value that we're going to first have. Then, so I'm going to go ahead and input these two equations, f1, f2. So we have f is equals to, f1 will be r1 plus r4 times cosine theta 4. We know that theta 4 is q2 in our code, which is initial guess 1. So we're going to say q of 2 q of 2 means that we're calling the vector, the position q2 in the vector q minus r3 times cosine q1, which is theta 3, minus r2 times cosine theta 2. Alright, so this is the first row. Now the second row will be r4 times sine theta 4, which is q2, so sine q of 2, minus r3 times sine theta 3, which is q of 1, minus r2 times sine theta 2. So this is our function. We now need to take a derivative of that function. In other words, we're going to put the Jacobian matrix. So we have here the Jacobian matrix. Solve it right here. So we will say df equals to r3 times sine q of 1, and in the first row, second column is negative r4 times sine q of 2, and these three dots is simply that I'm saying that I need to start from a new line without breaking up the equation. So the MATLAB code does not read these three dots that you put in your code. Now we're going to put this equation, negative r3 cosine theta 3, so negative r3 times cosine q of 1, and r4 cosine theta 4, r4 cosine theta 4, which is q2. Alright, so now we have the function and the first derivative. So now we're going to go ahead and implement the Newton-Raphson formula. So it will be q is equals to q minus the inverse of df, first derivative, multiplied by f. We're going to start our iteration to be equals to iteration plus 1, incremental of 1 iteration, and let's see if it's running. We have an error somewhere. Oh, there seems to be a semicolon. Oh, I did a typo here. This needs to be q1. Alright, so the code is working for the initial configuration. Now we're gonna print these values to see how are we doing. So fprintf we'll say iteration and again we're gonna store the directory of the iteration, and we're gonna print theta 2 and theta 3 3 we're also going to print the value of f. So as you can see, we have the iteration first, then theta 2, then theta 3. So we're going to start with storing the values of iteration. Then theta 2, actually this should be theta 3, and this will be theta 4. So we know that theta 3 again is q1, so we need to print q1. Now q1 is in radians, so we need to convert it back into degrees. So it's 180 divided by pi. And start a new line here. And then we're also going to print, the third thing we're going to print is theta 4, which is q2. So we say q2 multiplied by 180 divided by pi. And the value of f is the last thing that we need to print. So it's norm f. And let's run it and see the values. Awesome. So now we have the initial configuration values right here. So now we need to find the final configuration, what's theta 3 and theta 4 in the final configuration. So we're going to first store theta 3, which is the value that we're looking at. I'm going to store it right here. So we're going to say the initial position of the handle will be equals to q1. Okay, so now we're going to do the same exact thing, but we're going to start with a different theta 2 for the final configuration. Instead of 90, it will be 60. So we're going to go ahead and copy and paste all of that from here. So we're going to copy that and paste it here. And we're going to change theta 2. We're going to copy these two also. We're going to change theta 2, instead of 90, it will be 60. This is the final position that we're looking at. And as you can see in the problem, it said that we need to start from 1 and 3 for faster conversions. So you're going to change q to 1 and 3. And this will be the final configuration. Change this word to final configuration. And we're going to store q1, which is theta 3. After this configuration will be the displaced handle. So we'll be copy that line, paste it here. Now change that one into the final position of the handle. Final position of the handle. Let's see if it's going to run. Okay, it's running, have no problem. So now we need to display the actual value. So we're going to say the angular displacement will be equals to the displaced handle, or the final position of the handle, minus the initial position of the handle and we know that q of 1 is in radians, so we need to convert that back to degrees. So we'll say, oh, that will be multiplied by 180 over pi. We can run it, and that's it. Now we have the angular displacement of the mechanism. I hope that was helpful. We'll see you guys.